Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of a unit current electricity. So let's begin with today's class. In today's class we are going to discuss about the Ohm's law. So let's begin. As you know that what Ohm's law is all about, but in class 10 it was very introductory session about the Ohm's law. Only the basic detailed information were given. Now we are going to study in more detail Ohm's law. So let's begin with the Ohm's law. What Ohm's law says that at constant temperature for given dimensions of the conductor, the strength of electric current through a conductor is directly proportional to the potential difference applied across the conductor. You must consider this term at constant temperature. Even some of the material you might find that at constant temperature and constant pressure. At constant temperature and at constant pressure. For a given dimensions of the conductor, the strength of electric current through a conductor is directly proportional to the potential difference applied across the conductor. So the situation is something like this. Let's suppose this is a conductor and this is a voltage V. What it says that at constant temperature for the given dimensions of the conductor, the strength of electric current, whatever the current that is flowing through is, it is directly proportional to the potential difference applied across the conductor. So I is directly proportional to the V. Even you can understand this is V is directly proportional to the I. If I replace this proportionality constant with certain constant, then I can add a resistance R. V is equals to IR, or I can say I is equals to 1 by R of V. This R, this is proportionality constant, where R is the electrical resistance of the conductor. I again repeat that R is equals to V by I. It is a ratio of voltage to the current, but this is constant. This is constant. That means you cannot say that R directly proportional to the V. No, this is absolutely incorrect. Even you cannot say this R inversely proportional to the I. No, this is absolutely wrong. R is the constant. So if you want to change the R, you cannot use V or I. Yes, there are certain other parameters, there are certain other options are there to change the R, but it is absolutely not possible that if you are going to change the voltage while keeping the current constant, my resistance will be changed. No, this is not possible. Yes, please keep this in mind. Okay, so now what is the resistance? What resistance is all about? So let's define the resistance. It is the ratio of potential difference across the ends of a conductor and the current passing through the conductor is said to be the resistance of a conductor. So I can say R is equals to potential difference V divided by current I. So if I want to define a 1 ohm, I can say it's a if voltage or the potential difference is 1 volt and current is 1 ampere, then the resistance of a conductor is 1 ohm. SI unit can be written as a volt per ampere, but conventional unit is ohm, and mostly we are going to use ohm only. If I write the dimensional formula, it is M1 L2 T minus 3 A minus 2. You can easily derive this with R is equals to V by I. While V, I can replace its work done divided by charge multiplied by I, and Q can be replaced as I into T. So this is equals to I square T, and rest of the thing you know. So ohm is the resistance of a conductor is said to be 1 ohm if 1 ampere current passes through a conductor having a potential difference of 1 volt across its ends. Yes, that we know. I am sure that you have studied this in your theory sessions as well, but here we are just going to revise it. So if a certain points has been untouched, that can be covered. This is the symbol of resistance. This is how resistance can be represented. This is the symbol of variable resistance. Variable resistance means a value of resistance can be changed. It's a variable resistance. This is value of resistance can be changed. This is the variable resistance, and this is the symbol of resistance. I hope these things are clear. Is it? Now resistance of a wire depends on which parameters? Factors that influence the resistance of a wire. One, it is directly proportional to the length of the wire, that is R. R is directly proportional to the L. Second, it is inversely proportional to the area of cross section of wire. It's an R inversely proportional to the A. Next, it depends on the temperature of the wire. So if I want to use this, let's say this is relation number 1 and this is relation number 2, and if I want to write this 2 in a one relation, what I can have is that R is equals to rho multiplied by L by A. Resistance is equals to rho. Rho is a resistivity. So what I can have, I am having this relation R directly proportional to the L, R inversely proportional to the A, and if I want to replace this proportionality constant, I can introduce one of the constant, which is R is equals to rho into L by A. This rho, this is the resistivity. This is resistivity of material. This is resistivity of a material. This rho is the resistivity of a material. On which parameter it depends, we are going to discuss this in the next slides, but I hope these things are clear. So whatever we are going to discuss, that when we started the resistance, that at that point of time we were discussing that R is equals to V by I, and I was talking that if you want to change the R, you cannot change V, or you cannot dependent on I, but you can depend on this parameters. Yes, you can absolutely depend on this parameter. So if length of a wire increases, resistance will increase. If cross-sectional area of wire decreases, a resistance will increase, and vice versa. This is correct. I hope these things are clear to you. Is it clear? Yes. So let's have certain more additional knowledge about the Ohm's law. Yes, one very important topic, or one very important thing, is Ohm's law is neither a basic law nor a derivable one. Yes, this is not a basic law. Now question might arise in your mind is, sir, what is basic law, or how can I know that whether it is a basic law or not? When we want to understand that what the basic law is, we can take an example of Newton's laws. They are the basic laws. They is applicable to every object that do exist on the earth. That kind of law can be considered as a basic law, that can be applied to each and every object on the earth that is available. This is not the case with the Ohm's law. We can say that V is equals to IR is just an empirical relations. Yes, and microscopic Ohm's law can be expressed as V is equals to I multiplied by L by sigma into A, where sigma is the electrical conductivity of the material. Even you might know that in the previous class, in the previous session, we have derived this J is equals to sigma into E. This J was the current density. This is current density. This sigma is the conductivity. This is conductivity, and this E is the electric field. Even this is accepted. This is accepted as Ohm's law, or macroscopic nature, or microscopically this can be proved that this is one of the format of an Ohm's law. So please do remember this. in one of the school examinations or in board examinations, they just try that prove that J is equals to sigma E according to the Ohm's law and so on. So please remember this. Yes, I hope these things are clear. Now I know that what resistance is. Now let's define one more term. It's a conductance. It's basically it is the reciprocal. It's the inverse of the resistance, which we call as an conductance of a conductor. And this conductance can be written as G is equals to 1 by R. Now what I can write is 1 by R. Resistance is, it's a ohm. So this can be written as ohm inverse, or it is ohm inverse, it's a mho. If you see this, this is reverse of ohm. Yes, that's why it is called as a mho. Yes, it's a mho or ohm inverse or Siemens. Yes, dimensional formula of Ohm's law, it's an M minus 1, L minus 2, T3 and A2. Yes, you can calculate it very easily. Now limitations of Ohm's law. This is very important, because in certain medical examinations this has been asked even at the AIMS level. What are the limitations and which components does not satisfy the Ohm's law, and that all stuff has been asked twice in the AIPMT examinations, and once and twice, or probably once in the AIMS, as well as in JEE main examination. So please go through this very carefully. The limitations of the Ohm's law. Yes, we know that Ohm's law has been found valid over a large class of materials, but there do exist materials and devices used in electric circuits where proportionality of V and I does not hold, because according to the Ohm it should be an V directly proportional to the I. But there are certain materials or there are certain devices which devices does not satisfy this relations. That's why we have said that this is not a basic law, or this is not a fundamental law. Yes, the deviations broadly are one or more of the following types. First, V ceases to be proportional to the I, and the relation between V and I depends on the sign of voltage. So let's have a look at which are the components or how their graph look like. Let us look at this. If what I said is, if I is the current for a certain voltage and then reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction. So this is somehow which does not explain by the Ohm that this can be happen. As you can see in the graph, on the y-axis I have taken the potential difference, on the x-axis I have taken the electric current. The dotted line represents the linear Ohm's law, and the solid line is the voltage V versus current I for a good conductor. So you can see that from this line to this, both the lines are matching perfectly, but as soon as V is increasing or as soon as I is increasing, it is deviating from what Ohm has been said. I hope these things are clear. Is it clear? Yes. So there are certain situations and there are certain materials, we are going to just go through this, that they does not satisfy what Ohm has said. Yes. Now let's look one of the conditions. Characteristics curve of a diode. Now what is diode? Basically there are certain materials that we call as in semiconductors, and in semiconductor there are certain devices, semiconductor devices, what we call, one of them is the diode, another is the transistor. You are going to learn about all this in detail. It's a last second unit of class 12, but here we are just focusing on the which are the components that does not satisfy the curve, that has been given by the ohms. So if you observe this carefully, this is voltage and this curve represents the diode. Even you can observe this curve from this reference. Even this might help you. That let's suppose that this is the I and this is the voltage V. As you can see that for a certain voltage, this is something which is not completely satisfying the Ohm's law, because if Ohm's law has been satisfied, my curvature should be something like this. I hope these things are clear, that according to the Ohm, V and I should be directly proportional. But here first it is approximately 0, that up to certain voltage current is 0, and from then onwards it is increasing almost parabolically. So this is not the case, or this cannot be explained by simply the Ohm's law. One more situation in the reverse, this is the situation where we call diode is a reversed bias. This is reverse bias. This is reversed bias. Yes, in this situation current is changing like this. That cannot be explained by the Ohm's law. Yes, so this is one of the device. This is one of the device where Ohm's law is not satisfied. Let's look at the one more. Yes, this is variation of current versus voltage for gallium arsenide. This is gallium arsenide. What happened in gallium arsenide? It is again a semiconductor component. Basically it is made up with two different materials, that's a gallium and arsenide. But when I plot the characteristic of voltage versus current for a gallium arsenide, what I can observe is that you can see that from here to here it is approximately matching with the Ohm's law, but from this region from here to here, this is the non-linear region which cannot be explained according to the Ohm's law. Another, it's a negative resistance region. How this happens, why this happens, this is not the case at this point of time. But currently we are just interested in discussing that this is the situations, or there are certain materials which does not satisfy the Ohm's law. I hope these things are clear. So this is the negative resistance region, and this is again going to increasing something like this. So these are materials which does not satisfy what Ohm is said. I hope these things are clear. So these are certain limitations which cannot be explained by the Ohm. So what I can understood from this observation is that relation between voltage and current is not a unique one, because there is more than one value of V for the same current I. Even a material exhibits such behavior is gallium arsenide. There is more than one value of V for the same current I. Even if you can observe this again and again, that let's suppose take one of the voltage, that let's suppose this is the voltage and this two voltage are having a different currents, or this for this current the value of an voltage would be a different. So even this is possible. According to the Ohm, this is not possible at all. So Ohm's law is valid only for linear conductors. Please, this is limitation of an Ohm's law, that Ohm's law is valid only for linear conductors in which V versus I ratio is constant. And this is the case when we are talking about the metals only. So if it is a metal, we can absolutely apply Ohm's law, and Ohm's law will be absolutely valid and is applicable when it is a case of metals. But if it is not a metal, if it is a semiconductor, if it is an insulator, you just cannot apply Ohm's law directly. Yes, so this is one more time I want to emphasize on this, that Ohm's law is not a fundamental law like a Newton's law, as it is not obeyed by all the substances. Or we can say it is just an empirical formula to find the potential difference across the conductors. Now I hope you are clear with this relations, this limitations and this applications. So let's look at certain questions. Go through this quickly. What this is, at constant temperature for given dimensions of a conductor, The strength of electric current through a conductor is blank to the potential difference applied across the conductor. What does Ohm's law say? It says V directly proportional to the I. So directly proportional should be the correct answer. Did you get it right? Yes. Do you have same answer? Great. Next, the symbol of variable resistance. Yes, this is the symbol of variable resistance. What is this? This is simply the resistance. It's a value of, it's a fixed resistance. What we say, this is the fixed resistance and this is the variable resistance. What is this? Do you know this? Yes, it's an inductor. This is the symbol of inductor. Yes. So I hope these things are clear. Is it clear? Any doubts? Any doubts? Okay. Let's look at the ohmic and non-ohmic conductors. So what is ohmic conductors? One, we say it's an ohmic conductance. What we mean is these all the substances which obey the Ohm's law are called as the ohmic conductors, such as the examples is the metal. For linear or ohmic conductors, I versus V graph are straight line and which passes through origin as shown below. Look at this. This is the y-axis, this is the x-axis. I have kept voltage on the x-axis. I have kept conductor, that means electric current, on the y-axis. And if I take a slope of this, I know that, even you must know that slope is the delta y by delta x. So here it is a delta I divided by delta V. It's a 1 by R, and as we know 1 by R, it's a 1 upon resistance, which is conductance. So it is a G. If I plot the graph such like that on the y-axis it is the potential difference and on the x-axis it is the electric current. So if I plot this graph and it's a constant slope, if I take a slope it would be a resistance. So this kind of substances which obey, which satisfy the Ohm's law are known as the ohmic conductors. Now let's look at the non-ohmic conductors. That means substances which do not obey Ohm's law. This all are considered as a non-ohmic conductors, such as electrolytes, thermionic valves, thermistors, semiconductors, vacuum tubes, transistors, etc., etc. All those components which are made up with or with the help of semiconductors can be considered as non-ohmic conductors. Let's look at some of the quick examples. A thermistor is a non-ohmic device. What is thermistor? How do it work? Where does it work? At this point of time it is not our concern. Our concern is that there are certain materials which does not satisfy Ohm's law and we just want to identify those people. Yes, so thermistor is one of them. This is the characteristic of thermistor. It's a voltage versus current characteristics. As you can see that for different values of current, voltage could be the same. Look at this. There's 3 points. Yes, at every point voltage is same, but the current is different. So this is one of the device and it is the best example of non-ohmic components or non-ohmic devices. Yes, let's look at the VI curve. It's a voltage versus current curve for a semiconductor PN junction diode. Yes, this is the voltage, this is the current. Look at this, from here to here we can say it might be directly proportional, but from here onwards it is a non-linear region. Even in this situation this is the non-linear region, so this is not satisfying Ohm's law. One more relation, this is the relation for vacuum tube. Yes, this is the voltage versus current graph for a vacuum tube, and as you can see, if you choose any of the section, any of the section, this are not satisfying the Ohm's law. So this all are the elements which are the non-ohmic substances. So ready for the questions? Are you ready? Let's look at the question. First, Ohm's law is applicable to ohmic conductors, non-ohmic conductors, both ohmic and non-ohmic, and vacuum tubes. Yes, it is applicable to ohmic conductors only. Next, the resistance of a conductor is, okay, so dependency are directly proportional to the L, are directly proportional to the 1 by A. So now what the options are saying, it is inversely proportional to the length. No, it is directly proportional to the length. Directly proportional to the square of the radius. No. Inversely proportional to the square of the radius. Yes, it can be considered. How? Let's look. It's a R directly proportional to the 1 by A, and when I say R it directly proportional to the 1 by A, I can say it's a pi R square. So resistance is inversely proportional to the square of the radius. So this could be the correct answer. Yes, I hope those things are clear. Is it clear? Yes, is it clear? Great. So ready for the question? Let's find it out. That suppose this is voltage, this is current, and if I plot this, it is something like this. This is 0 volt or 0 ampere. This is I, this is 10 ampere, this is 5 volt. So what they asked that find out value of resistance for given graph. So how could I find it out, the value of an resistance? I know that R is equals to V divided by I, and when I say R is equals to V divided by I need to perform a slope of the given graph. It's a slope of the given graph. How could I solve this? It's a delta V divided by delta I. So delta V, it's a 5 minus of 0, divided by delta I, it's a 10 minus of 0. So this is 5 by 10, and when I say 5 by 10, it's a 1 by 2, or rather I say it's a 0.5. Yes, one more question. This graph is for ohmic substance or non-ohmic substance? Yes, as you can see that voltage and current, these two are seems to be directly proportional with each other. So this graph might be drawn for the ohmic substance. I hope these things are clear. Is it clear? This is the graph for the ohmic substance. Is it clear? Are you sure? Okay, so let's move to the next topic, resistance and specific resistance. So first let's begin with the resistance. What is it? When we say that resistance dependency on this many things, it is directly proportional to its length. We can write like this, it's R directly proportional to the L. It is inversely proportional to the area of cross section, so it is R inversely proportional to the A. One more thing, it depends on the material of the conductor, that means copper or aluminum or silver. This all are having different resistance because it depends on the material of the conductor, as well as it depends upon the temperature of the conductor. How it behaves, we are going to see it in the coming sessions, but it depends. So it depends primarily on 4 things. First, this depends on the length of a conductor. Second, this depends on the cross-sectional area, but inversely proportional to the cross-sectional area of a conductor. Third, it depends upon the material of a conductor, and one more thing, it depends upon the temperature of the conductor. These 4 are the factors on which it depends. So if I want to just summarize this in a one relation, what I can write is that R directly proportional to the L by A, And if I want to remove this proportionality symbol, what I can add is it's a one of the constant, and this is the rho, which is we call as a resistivity. Now let's look what resistivity or specific resistance is. Here rho is the specific resistance or resistivity. We have this relation R is equals to rho multiplied by L by A. So from here I can have it's a rho is equals to R into A by L. Value or unit of R, it's an ohm. Unit of an area, it's a meter square. Unit of a length, it's a meter. So this is ohm into meter square by meter, which is ohm into meter. Yes. So as we have already discussed that copper wire, aluminum wire, and both must be having a different resistance. Both must be having a different resistance because it is made up of the different materials. Now this is all about the resistance, but on which parameters resistivity depends. Let's have a look. First we are going to define the specific resistance, and then we will switch to the certain additional information and their factors on which it depends. So let's begin with the definition of resistivity. Even it is said as the specific resistance. So resistivity or specific resistance of a material is numerically equal to the resistance of a conductor of unit length having unit area of cross section at a given temperature. How I have defined this? Let's have a look. It's R is equals to rho L by A. So from this, rho is equals to R into A divided by L. So if I make area of cross section as a unit, let's have a look. Unit area of cross section. If I make length of a conductor unit, a conductor of unit length, then resistance is equal to, or I can say resistance is numerically equal to resistivity of a conductor. So if I take A is equals to 1 meter square, length is equals to 1 meter, then resistivity is equals to the resistance, or I can say it's a numerically equal. Yes. Now let's learn something more with respect to resistivity. This topic is very, very important because it contains a certain definitions and certain very specific information that has been asked or at different phases of the examinations. So please learn this, all the things, learn this every material very carefully. So let's begin. First, resistivity is the specific property of a material, but resistance is the bulk property of a conductor. Resistivity is material dependent property. It is material dependent property. But resistance is the bulk property of a conductor. Yes, resistivity does not depend, it's an independent of the dimensions of conductor like length or area of cross section. So rho does not depend on the length, even does not depend on the cross sectional area, neither directly proportional nor inversely proportional. So it does not depend on the length, it does not depend on the area of cross section, but it depends on the first, depends on the nature of the material of the conductor. It depends on the temperature, second, and third it depends on the impurity. So please remember, rho depends on first material, second temperature, and the third impurities. It depends on these three parameters only. It does not depend on the length of a conductor, or it does not depend on the cross-sectional area of a conductor. Yes, resistance of the metals increases by the addition of impurities, or resistivity of an alloy is more than the resistivity of its constituent elements. Please remember this thing, because in many practical applications we are using a certain alloys because they have a certain very specific capacity of heat providing capacity or heat absorbing capacity and something like that. So resistivity of a metals increases by the addition of impurities, and resistivity of an alloy is more than the resistivity of its constituent elements. Now, which are the elements that we are going to use? Let's have a look. That constant, manganese, and nichrome having the high resistivities. So as they are having a high resistivities, these materials are used for the standard resistance boxes, meter bridge, potentiometer wire, etc. Now next, silver, copper, aluminum, all these are the material which are having a very low value of resistivity, and that's why this material, silver or copper or aluminum, can be used in making electrical cables and connecting wires. Fuse wire, I hope you understand what the fuse is. Do you understand fuse? Yes, it is just the beginning part of any electrical circuits. Yes, if you see the household's connections, a very beginning part of the our household connection is a fuse, and fuse wire is made of tin and lead alloy. Please remember this, have been asked in the AIMS examinations. And because it should have a low melting point and low resistivity, so an alloy has been formed, and that alloy uses tin and lead, because we want that fuse wire must be having low melting point and low resistivity. One more, the elements of the heater coils are made up of nichrome wires, which has a nichrome is having a high resistivity and high melting point. I hope you understand what the heater coils is all about. Yes, they are using at different places. In previous times, even in certain sections of country, even at this stage, people are using a water heater. It's a one kind of cable coil kind of thing, and it is used to boil the water. Even electric kettle is there. Even every kettle is using heater coils only. Electric ironing is there. Even the electric irons are there which are using the heater coils. So everywhere wherever we require a heating applications, we are using this kind of heater coils, and that is mostly made up from the nichromes, because nichrome is having a high resistivity and high melting point. And last but not the least, a filament of electric bulb is made up of tungsten, which has low resistivity and high melting point. Even it is not melting at very high temperature. So because of this quality, it can be used, and it is using to made a filament of an electric bulb. Yes, I hope these things are clear. Yes, these are theoretical sessions, but these are very important theoretical points. It might possible that you have learned all this in your school sessions, but this is will help you to score a good numbers in a theoretical questions. So please go through this. Please note down this in your words in your notebooks. Please do this. Okay, now let's look at the conductivity. We have been done resistivity, and now we are switching towards the conductivity. Basically it is the reciprocal of a resistivity that we call as an conductivity. SI unit, it's an ohm into meter inverse, or we can say it's a Siemens per meter. We know that R is equals to rho into L into A, and cross sectional area, which can be written as pi r square, or even D is equals to R by 2. I'm talking about the diameter. So this is 4 rho L into pi into D square. Yes, is it clear? So from this, if I required a resistivity, then it would be R multiplied by pi D square. R multiplied by pi D square divided by 4 into L. 4 into L. This is the resistivity, and my conductivity would be simply 4L divided by R multiplied by pi into D square. So from these relations we have a clear-cut idea that we have a dependency of resistance on these three parameters. One, length of a conductor. Second, area of a conductor. And when we talk about the area of a conductor, we say it's an inversely proportional to the square of the radius, and inversely proportional to the square of the diameter as well. Is it clear? So shall we move to the some of the applications which is asked or very frequently? Let's have a look. What we know that R is directly proportional to the L, R inversely proportional to the A, and R is equals to rho into L divided by A. Now what they ask is, let's have a look, that if wire has been stretched so that its length increases and its new length is twice of the initial value. Find out value of resistance. Find value of new resistance. Here assume that previous value of resistance is R ohm. So go through this data very carefully. What they says if wire has been stretched so that its length increases and its new length is twice of the initial value, then find out the value of the new resistance. And we have been provided that the previous value of the resistance is R ohm. Is it clear? Yes. How could I do this? So let's look. The situation what I understand is something like this. Let's suppose this is the length of a conductor. Initially this is, if I stretch it, this will become something like this. But if length increases, if length of a conductor increases, then cross-sectional area of a conductor decreases. That means volume of a conductor remains the same. I hope you understand this, that length is increasing but cross-sectional area must be decreasing. And if it is decreasing, that means volume of a conductor must remain the same. This is the case. So if volume of a conductor remains the same, what I can write is that R is equals to rho into L by A. Yes, this is the situation. Now what I can write, it's an R2 divided by R1. This should be is equals to rho multiplied by L2 by A2 multiplied by, this is rho multiplied by L1 by A1. This rho has been gone, and this is L2 by L1 multiplied by A1 by A2. This is the relation. Now I know one more very important aspect, that volume 1 must be is equals to volume 2, because volume remains the constant. And if volume 1 is equals to volume 2, it is A1 L1 should be is equals to A2 L2. And if I use this in a very intelligent manner, it's an A1 by A2, that should be is equals to L2 by L1. So this is, if A1 by A2 is equals to L2 by L1, let's use this, so that R2 by R1 should be is equals to L2 by L1 multiplied by, let's replace the A1 by A2 by L2 by L1. So this is L2 by L1 whole square. Or I can say a very important parameter, R directly proportional to the L square. But this has been written if and if volume remains constant. This can be written, but for this to be true, volume of a conductor must remain constant. If volume is constant, I can use this. If it is not, I must go with the R directly proportional to the L. I hope these things are clear. Is it? So in a same manner, what I can write is for the cross-sectional area as well. This was previously, it was for length, now it's for cross-sectional area. What I know R2 divided by R1. This is equals to rho multiplied by L2 divided by A2 multiplied by rho multiplied by L1 divided by A1. This rho has gone, and if it has gone, it would be an L2 by L1 multiplied by A1 by A2. One more thing that we know, it's a volume of 1 must be equals to volume of 2, and that's why it's an A1 L1 should be is equals to A2 L2. So L2 by L1, this is equals to A1 by A2. So that should be is equals to L2 by L1 multiplied by A1 by A2. Let's replace L2 by L1 with the help of A1 into A2. So A1 A1 divided by A2 multiplied by A1 into divided by A2, it's an A1 divided by A2 whole square. So what I can write it's an R directly proportional to the 1 by A square. It's inversely proportional to the square of the cross-sectional area of a conductor. This is the same case when volume remains constant. If volume is constant, you can use it. If volume is not constant, please do not use this. One more relation, I know that area is equals to pi r square. So this R directly proportional to the 1 by pi into r square whole square. So it is inversely proportional to the 4th power of a radius, where r is the radius of a wire and this r is the resistance. Same way I can write like this for the diameter as well. This is for diameter. Yes, here I am writing this, all this, when volume remains the constant and in a proportionality symbol, so no need to add the constant. Now this all are the relations that have been derived. Now let's get back to the question, because we were supposed to do this and we have derived this relations. So what it says, again read this: if wire has been stretched so that its length increases and its new length is twice of the initial value, find out the new value of a resistance. So what I know is R2, let's say this is the new length, divide by R1 is equals to L2 by L1 whole square, because here volume remains the constant. As the data said, L2 should be is equals to 2L1. So this should be R2 by R1. This is equals to 2L1 divided by L1 whole square. And if I cancel this, it is 4. So this is R2 divided by R1, which is equals to 4. So I can write it's an R2 should be is equals to 4 times of R1. So if initially value was R, the new resistance will be equals to the 4 times of the previous value. So this R2 should be equals to 4R. I hope these things are clear. Is it clear? Is it clear? Are you sure? Are you sure? Great. Now ready for the next questions? Are you ready? Let's have a look. If a conductor is compressed such that its radius is increased by twice of the initial, find out new resistance. Find out new resistance of conductor. So here they have not directly said that volume remains the constant, but you need to take decision that shall I consider that my resistance remains or my volume remains constant or not. Yes, because they said conductor is compressed, so situation maybe look like this. Maybe this is the initial conductor, and when I compress this, it might look like this. Yes, so as you can observe, this is the initial length, and this is the initial cross-sectional area. This is the final cross-sectional area, and this is the final length. Yes, so as I compress it, its cross-sectional area increases and its length decreases. So what I can write, it's an R2 by R1. That should be is equals to A1 by A2 whole square. And what I can write, it's a pi into R1, pi into, I should use a smaller. Yes, so this is pi into R1 square divided by pi into R2 square whole square. This has been gone and only the term remains. It's an R2 divided by R1. It is equals to R1 to the power 4 divided by R2 to the power 4. Now they said that its radius is increased by twice. Radius is increased by twice. So twice has been increased. So this they have given that this is R1 to the power 4, and this R2 can be written as 3 times of R1 because by twice it has been increased. So this is 3 R1 to the power 4. So this is R2, this is R1. R1 to the power 4, R1 to the power 4 has been gone. 1 by 3 to the power 4. Now 3 to the power 4. 3 cube, it's a 27, and 3 to the power 4, it's an 81. So this is 1 by 81. So R2 is equals to initial resistance R divided by 81. This should be the final answer. Is it clear? Is it clear? I hope these things are clear to you. Is it? Great. Ready for the next question? Ready? Let's have a look. If length of a conductor is increased by, if length of a conductor is increased by 2% while cross-sectional area of a conductor is decreased by 3%. Find change in the resistance of conductor. This is what you require. As the data set, a length of a conductor is increased by 2%, but cross-sectional area of a conductor is decreased by 3%. We need to find out the change in the resistance of a conductor. Now, how should you do this? First, tell me, can you consider that your voltage remains the constant? Can you consider it? No, absolutely not. Because they said that length is increased and cross-sectional area is decreased by different percentage. Yes, so you cannot assume that your volume remains the constant. So you must stick to the basic relations, which is R directly proportional to the L and R inversely proportional to the A. Now, they have said that the change they have given, increased, decreased, this all are the changes. And these changes are less than 5%. If you observe this very carefully, this all changes, that means whether it has been increased or whether it has been decreased, this all are the changes by less than 5%. So we can use the relation of errors, but by using certain intelligence. That means if I write the relation delta R by R is equals to delta L by L plus delta A by A, is it correct? Is it correct? Let's have a check. That what it says, the length of a conductor increased. So if L increases, R must be increases. So yes, if this is positive, this is positive. Now, cross-sectional area of a conductor is decreased. If this is decreased, this has been increased. So this is additive. Yes. Now, it's in delta R by R. Again, this all things are in percentage only. This is increased by 2% and this has been increased by 3%. So this is 5%. And as this is the positive number, so my resistance has been changed. My resistance has been changed by 5%. I hope these things are clear to you. Yes? Yes. Is it clear? So, ready to move the next question? Let's have a look. If radius of a wire changes by 3%, find out change in the value of resistance. Assume that volume of a conductor remains constant. Yes, you need to assume this. What they said? They said that radius of a wire changes by 3%. That radius is changed by the 3%, and you need to change. You need to find out the change in the value or change in the resistance. And it has been said that volume of a conductor, this volume of a conductor remains the constant. So if it remains the constant, what I can have is that R inversely proportional to the fourth power of a resistance, fourth power of a radius, sorry. So it's an delta R by R, that can be written as a 4 into delta R by R. As it has been changed by 3%, this is 4 multiplied by 3%, this is 12%. There would be a change of 12%. We are not sure that whether it will increase or decrease, because radius they have provided only that it changes. If they said it increases, this must be decreases. If they says it decreases, this must be increases. I hope these things are clear. Yes. So can you do this kind of question? Are you sure? Are you sure? Okay. Let's have a look, a summary kind of thing of all the situations that we have discussed. That look at this. If a conductor is stretched or elongated or drawn, then the volume of the conductor is constant. And if this is the situation, what I can write, it's an R is equals to rho L by L, and this is R directly proportional to the L square. Same way R inversely proportional to the A square, and from this what I can write, it's an R inversely proportional to the A square that I have written over here. R inversely proportional to the fourth power of radius, as well as R inversely proportional to the fourth power of diameter. One more thing, that if I replace this term with R is equals to rho into L square by V, I can write like this. Would you like to see it, that how this can be written? Let's have a look. This is the situation, R is equals to rho into L by A. Yes, this was the situation that R is equals to rho into L by A. Now if you multiplied both the sides, by L, this should be rho into L square divided by area into length. It's a volume. Now density, I should write it as a D. It's a density is equals to mass by volume. So to replace the volume, I can use it's a mass by density. So this can be written as rho into L square divided by volume. It's a mass divided by density. So you can write like this, it's a rho into L square into D by M. Even this can be, if it has been multiplied and divided by the area, then I can have this relation, rho into V by E square. So this all are the relations, which are very useful and which is very handy so to calculate the questions. Let's look one more short form of this. For small changes in the length or radius during the stretching, when we say during the stretching, that means they want that you must consider your volume as a constant. Then you can write like this, it's a delta R by R, which is 2 delta L by L, as it is inversely proportional, R inversely proportional to the A square. That's why a minus is written. Even minus 4 delta R by R. Even if diameter has been asked, it's a minus of 4 delta D by D. Yes, and last but not the least and very important, let's look that one of the cylindrical conductor is there, something like this. And if this kind of conductor is there, you have been asked the resistance. It's let's say this is L. The radius of an outer cylinder, it is R2. The radius of the inner cylinder, it is R1. What do you want? You want the resistance. So my basic formula is R is equals to rho into L by A. Now this is equals to rho multiplied by L divided by area. Now area is pi R square, and pi into external radius, a square of the external radius minus square of the internal radius. This is pi into R2 square minus R1 square. This is the resistance. I hope these things are clear. So can you do this kind of questions? Are you sure? Can it be done? Okay, so let's wind it up this session over here only. Please practice this kind of questions, as many questions as possible. Thank you. Have a good day. Take care. Bye bye.